Hello viewers, welcome back to the course on matrix computation and its application. So today we are going to discuss a very important application, that is the best approximation using least square method. Now suppose we have some data. This is my x-axis, this is my y-axis, and suppose some data is given to me. Suppose I take one data point here, then I have this point, something like this one. So this is my, I can write this as x1 y1 point, this is x2 y2, and this is in the end I have x and y. So these points are the random points that is given, and I don't know that where they lie. They may lie on a straight line, or they may be spread over the given xy plane. So in this case, now the question is that we want to fit a line passing through these points. So I have written that the passing through these points. So I know that I can fit a line that is passing through all these points. So this is possible. This is possible if all the points are collinear. That is, all the points lie in a line. So in that case, how will we find out that, what we are going to do that, let us take a line, that is I am writing as y is equal to, maybe I write a x plus b. This is my line. Now I will substitute the first point here. So I will write a x1 plus b, and suppose this is equal to y1, a x2 plus b, that is equal to y2, and from here I will get a xn plus b, that is equal to yn. So I don't know whether these points are collinear or not, but I want to approximate these points with a line. So I want to fit a line that is passing through this point. So, and it will pass through these points only when it is collinear. Otherwise I want that the line, how it is going to pass from this one. So this is I want to fit. So I can say that we want to fit a line from the given data for given data points. Maybe I can write this way. Now, so let's I don't claim anything, I will do with this one now first. So I want to fit a line, so I have taken a line, the equation of a line, and then I put the value here, and suppose this is equal to this value. Now from here, if you see, I can write this in the matrix form. So I will get the value here, this is my x1, x2, xn, and this is 1, 1, 1, 1, all these ones, and here I can take a, b, and this is equal to y1, y2, yn. Now if you see from here, So, I can write this as a matrix A, and this is I write a vector. So, this matrix is, if you see from, it is dimension n cross 2, this is 2 cross 1 and this will be n cross 1. So, this matrix is of order of dimension n cross 2. Now, we are assuming here, so assuming here we are assuming that all xi's are distinct. It means xi is not equal to xj for any ij. It means they all are distinct. So, from here if you see, then this is a system of equations. So, I can write this as A, and maybe I can write this vector V is equal to y. This one I can write. Now, from here if you see, I am taking the second column is 1 1 1 and the first column is x1 x2 x3, and I am saying that all these are distinct. Now, from here I can say that the rank of A is 2. Now, we have rank of this matrix 2. So, this is the basically this system is, I can say that number of equations are greater than number of variables. The number of variables is only 2. I want to find the value of A and B for this line. Okay. So, I assume that this is the line which is going to fit for the given data. So, I need to find the value of A and B. Now, if this line is there, I put the value of x, all these x coordinates, and suppose it is equal to y1, y2, yn. Okay. So, this is the system we get where the number of equation is greater than equal to, I can say, the number of variables, and this system is called overdetermined system. System of equations. So, rank is 2. Now, from here, if you see from here, then this is equal to, I am writing A, and this is x1, x2, xn. I can write this as a B, 1, 1, 1, and it is equal to y1, y2, yn. This one. Now, two things happens. Now, in this case, because it is the number of equations are greater than number of variables. So, this system, I can write this system as, this is my equation number 1, and I can write this as 2, this I can write as a 3. Now, system 2 may have solution. Now, the question is that when it can have the solution. Now, if the vector, so if the vector this one y1, y2, yn, this is right hand side vector, I just take the transpose here. If the vector this belongs to column space of this vector, the column space of this vector x1, x2, xn and 1, 1, 1, because if you see this one, it belongs to Rn. So now if this vector belongs to the column space of this one, then the system has solution. And in this case, I know that this matrix is of dimension n cross 2, so its rank cannot be more than 2, but here the column vector are linearly independent, so the rank of this matrix is 2. Now from here we can say that if the vector this belongs to the column space, then the system has solution, has in fact unique solution. And if this is there, this is possible only when all the points, all the data points I can say, and this is possible only if all the data points are collinear. It means this system is going to have the solution when all the data points will lie in a line like this one. If I see this one, so these points I have taken all lying in the line. So if I fit a line from these points, then this system is going to have the solution. All the points lying completely on the line, these points are completely on the line, not away from the line. This is my line, and this is, I can write that this is y is equal to ax plus b. So if this system has a solution, then all the points are going to lie on the line. Now, but in general our data is spread over the whole domain xy. They are not lying on the xy in a line, because these data points are coming from some experiment. So in this case, now if the data points are not collinear, that is they are sparse, the points are spread all over the domain, the data points are spread in the xy plane. So if that is there, which implies that the system a v is equal to y is inconsistent. Inconsistent means this system is not going to have the solution. So that is there. Now, so in that case what we are going to do? Now it means that in this case a v, if I take y and taking its norm, that is basically we are dealing with the, so if now if this is 0, then system is consistent and having unique solution. But if we take a y minus y and suppose this is not 0, then the system is inconsistent. So, this system I cannot solve with the method. So, you can see from here that basically this is what it is, a error. Now, from here what we are going to do is that if you see from here, then I can write this as, maybe I can write y minus a v. This, if you see square, this is equal to y1 minus a x1 plus b, because this is giving you the error basically. So, this is basically the error. This is basically the error. So, this is equal to square, because I am taking the 2 norm here. So, then it will be equal to y2 minus a x2 plus b and yn minus a xn plus b. This one I can take. And if you see from here, then this is, I am taking the, because what I am going to do is that, suppose I take a line passing through this point. So, the error will be just, this will be the error, this will be the error, this will be the error, this is the error corresponding to this x. Actual value is this one, and by the line we are consuming this one. So, it is my E1 basically I can write. So, from here if you see, then this is equal to E1 square, E2 square and En square. Now, so now we come to know that I cannot fit a line which is passing through all this point. So, but that is not possible. So, now we want a line which is passing through, which is passing close to all the points. This is what I can do. So, from here it is y minus a v square, that is equal to this one. So, now what I want, that we want to minimize y minus a v. So, I want to minimize this one, and I will minimize over the value of a and b, because that value I have to find the coefficients in the line AB, ax plus b. So, I want to minimize this error basically. So, this is called the minimizing the error. So, if I able to minimize this one, then I will get a line which is passing close to all the points. And if you see now this one, then this method is called, we have least square method, the least square solution. So, why it is called? We are taking the square. So, this is the square of the error. If you see, then this is the square of the error, and I am finding the minimization. So, I am finding the least of all this one. So, that is why this name is called the least square method. So, our main purpose is here to minimize this error term, the square of the errors. So, I want to do this one. So, that is called my least square method, and this is the best approximation that is we discuss now. So, let us I just give one example that how it is happening here. I just take one example. Suppose I take a line, suppose I have a point 1 1, 2 2, maybe 3 3, 4 4, I have 4 points, and I know that these points are collinear points. The 4 points are there, but if you draw these points, then it is, suppose one point is here, another is here, another is here, another is here. So, all the points lying on this line. So, I know that this is a line y is equal to x. Okay. Now, I take that so let us take a line y is equal to ax plus b. Now, from here I can write, so a1 plus b is equal to 1, a2 plus b is equal to 2, a3 plus b is equal to 3, a4 plus a into, so this is into b plus 4, and from here I can write a matrix 1 2 3 4 1 1 1 1. This is the matrix, and this is my AB, and that is equal to 1 2 3 4. Now, from here if you see, I can solve this system, because here if you see from here, then this vector can be written as a linear combination of these two. So, this vector lies in the column space of this matrix A. And now, also if you see from here, I can solve it very easily by the standard method. I can write the augmented matrix So, this is the augmented matrix I can write 1 2 3 4 and then it is 1 2 3 4 and I can make this. So, this is 1 1 1. Now, if I multiply by -2 and add here, so it will be 0, -2 plus 1 minus 1 and 0. Now, it is 0 0 -3 plus 1 minus 2, this is also 0 and this is basically -3 and this is 0. And from here I will write this as 1 1 1 and this is 0 1 0 and then I can write 0 0 0 because I know the rank of this matrix. So, rank of A is same as rank of augmented matrix. I can write like this one. So, the system is consistent, and if you see from here, then if I want to find out the solution, so the solutions will be A plus B is equal to 1 here and then I get B is equal to 0. So, from here I will get A is equal to 1. So, that gives me solution that A is equal to 1, B is equal to 0. So, I get the line A is equal to x, and I already know that this is going to the solution. So, this is a collinear points and we are able to solve this point. Now, suppose we have points, maybe I just take point 0 1 1 2 and 2 4. Suppose I take these points, I just take the 3 points and I just take the equation. So, now I get A into 0 plus B is 1, A into 1 plus 2 plus B is equal to 2 and A into 2 plus B is equal to 4. I just taken this line. So, I assume a line that is y is equal to Ax plus B, and from here I will get the matrix that is 0 1 2 1 1 1 A B, and this is equal to be 1 2 4. So, this is my system of equation, and I know that this matrix is having the rank 2, no problem. Now, from here I write its augmented matrix. So, that is I am writing 0, 1, 2, 1, 1, 1, and the right hand side column is 1, 2, 4, 1, 2, 4. That is my augmented matrix. I will reduce into row echelon form. So, reduce this one, it will be, now in this case I just swap the first and the second row. It is 0, 1, 1, 2, 1, 4, and now from here I can write, I can make it echelon form. So, I want to reduce echelon form. So, this one I want to do. Now, it is already 0. So, I will 1, 1. Now, I want to make this 0. So, minus 2 and adding here. So, minus 2 plus 1 minus 1, and minus 2 is minus 4 plus 4, that is 0. So, from here if you see, now I am writing 1, 1, 2, 0, 1, 1. Now, adding, so I add this one, so it will be 0, and adding here it will be 1. So, I can say from here that the rank of augmented matrix is 3, but the rank of A is 2. If you see, this is the A matrix. So, rank is 2, and the whole augmented matrix, the rank is 3. So, in this case I can say that the system is inconsistent. So, this system is inconsistent, I cannot solve this one. So, it means that we cannot find a line which is passing through all this point. Okay. So, from here that we find that the system is inconsistent. So, now our next step is we need to find a line. So, we need to find a line which passes closest to all the data points. So, this is what I need to do to find out the line fit. So, this one we need to do. So, how we can do this one, because I found that the system is inconsistent. So, if the system is inconsistent, then how I am going to solve this system. So, that is the one of the main question for finding this system or the solution of this one. So, now we are going to introduce a important thing is that now if you see from here, I have this matrix, this is my matrix. So, I have my matrix here. Now, we have A V is equal to Y, and my A is 0, 1, 1, 1, 2, 1, and my Y is 1, 2, 4. Now, I know that these two vectors, so this vector and these vectors are linearly independent, okay, and also so this vector 0, 1, 2, the first column. So, I can take transpose here, and 1, 1, 1 transpose, this belongs to R3 and are linearly independent. It means that they, so this spans, if I take these vectors and finding their span is a subspace of R3. So, this is a subspace of R3 basically. Now, if you see from here that this is a subspace 0, 1, 2, okay, this vector and 1, 1, 1, they are linear independent, is a subspace of R3. So, let us write here. So, I just take the 3-dimensional plane. So, 3 dimensions we have, this is x, y, z, and suppose this is some plane. I just make a plane here. So, suppose this is a subspace made up of these vectors, because it will be a plane. Now, I know that this vector, so this system is inconsistent, which implies that y, this vector 1, 2, 4 does not lie in the column space of the matrix A. It means this vector 1, 2, 4. So, if I take any point, so this 1, 2, 4 is not lying on this plane in this subspace. So, it may be somewhere here. Let us write that this is my vector 1, 2, 4, like this one, and this is the subspace S. So, I just write it S. This is a subspace, because if this point lies in this plane, in this subspace, then the system will be consistent, but now we know that this is inconsistent. So, it is not lying here. So, what is we are going to do is, now we are going to take the projection of this vector on this plane. So, we are going to take the projection of this vector over this plane. So, that this is right angle. So, this is, suppose my, I have a system A v is equal to y, then, so this is my, suppose y. Now, this is the projection of this vector on this space. So, this is, suppose my new y, I call it y hat. So, now I can say that the y hat is a projection of y on the subspace S. So, now we need to find that how we can take the projections of this space, subspace, projection of this vector on the subspace S. So, this is what we have done in the theory. So, now we do this one in generalization. So, let us do how we can take the projection. Now, we do for generalization. So, how to take projection of y on the subspace S. This one we want to see. Okay, so let us see that how we can do this one. Now, so we just take the generalization. I have A, okay, I have some, maybe I just take x is equal to b. I will write this a general space. So, let us take this one. So, proof. So, here we are going to do. Let us assume a system of equation Ax is equal to b, where A is something like having 2 columns only, because I know I always having 2 columns. So, it is going to have the A1 and A2. So, this is the 2 columns is going to have, because in this case we have always n cross 2, and my x is 2 cross 1, and on the right hand side I have b, that is b1, b2, bn. So, this is n cross 1. So, always we are going to have. Now, I know that this vector is, now we know that B does not lie in the column space of A. So, that is does not lie column space of A. Okay. So, now I will just make some 3-dimensional space, and suppose this is my plane, space S is equal to the span of A1, A2, and suppose this is my x. I am just considering it in the 3 dimension, and we have a vector which is lying here. This is my vector b, and I take its projection here, and I get this vector. This is my projection vector. So, I call it maybe p, and this is my basically b hat, the new projection vector. So, this one I want to find, and I know that this is equal to error, this part. Now, we assume that A1 and A2 are Li, linearly independent, because they are always linearly independent. So, we assume here that they are linearly independent. So, the space subspace S is A1 spanned by A1, A2, and dimension of S will be 2 in this case. Now, that is okay. So, now once we have the projection, the b dash, then now we have our system, new system, that is new system, that is having the same x, but on the right hand side we have a new b. So, in that case we need to solution, and that solution will be a new solution, that is x hat I am writing. So, x hat is a solution of A x hat is equal to b. So, this is the solution of this one. Now, if you see from here, this is the error E. So, what is E? E is basically, if you see, that is b minus b hat, because this is b and this is b hat. So, it is b minus b hat. Okay. So, now from here, now we know that from this place I know that b hat is perpendicular to b minus b hat. and b hat I know that this is Ax equal to b. So, from here I can write that b hat is perpendicular to b minus Ax hat. I can write like this one. So, from here I can write, now from this b hat is lying in the subspace S. So, I can write that also b hat belongs to the subspace S, which implies that b hat can be written as some linear combination. I can write C1 A1 plus C2 A2. Okay, so from here I can write, so this one I can write that C1 A1 plus C2 A2, that is my b hat, that is perpendicular to b minus Ax hat. This one I can write. And from here very easily I can write that because this A1 and A2 already lying in this one, A1 and A2 are lying on in the subspace, and this vector error vector is perpendicular to the whole S, because this is making the right angle triangle here. So, this vector b hat is lying in the S space, and this vector is perpendicular to this one. So, now from here I can say that the A1 is also perpendicular to b minus this part, and A2 is also perpendicular to b minus a this part. So, if you from here I can write that A1 transpose is b minus Ax hat is 0. I am taking the dot product, so in the matrix form, and from here I can write A2 transpose b minus Ax hat equal to 0. Okay, so from these two equations I can write that the A1 transpose, I can write A2 transpose, that is, I just take, because my matrix is, if you see my matrix is A1 and A2, the column vectors. Now, I have A1 transpose and A2 transpose as row vectors. So, this is, if you see, that is equal to A transpose. So, I can write from here. So, this is my vector taking the dot product with this vector, and that is 0 0. So, this is my matrix A transpose. So, from here I can write that very easily I can write that this is equal to A transpose b minus Ax hat equal to 0. From here I can write this is A transpose, in the matrix form I can write, and that gives me that the A transpose b minus A transpose A x hat equal to 0, and from here I get that A transpose A x hat is equal to A transpose b, and this one now, since rank of A is 2, rank of A transpose A is also 2 and invertible. So, this will be invertible. So, from here I can write that my x bar will be A transpose A inverse A transpose B. So, that will be my approximate solution for the given system, this one. So, using this one I am able to find x hat. So, this is my x hat. Now, so from here you can see that, and if you see from here this is B hat, that is equal to A x hat. Okay, so from here now what is A x hat? So A x hat I can write as A transpose A inverse A transpose B. Okay. Now that is equal to B hat, because we have already seen. So this equation I can give the maybe I can give name 1. I have started from generalization. So this is my basically generalization I have started. So after that I got, maybe I should write it as 1. This is my equation number 1. Now this is 2, and I can write this as equation number 3. Now from here this is equal to this. So from here I can write a projection matrix P, which I apply on B, I get B hat. So where P is my matrix A transpose A inverse A transpose. So this is called projection matrix. So if I use this matrix on any vector, so what is it do? It will project that vector into the subspace made by the columns of A, that we have already seen. So that's why it is called the projection matrix. Now, so this is the projection matrix we have. Now we have some properties of a projection matrix, because if you see, then I want to find out what are the properties of the projection matrix. So let's see this one. So P is the projection matrix. So if it is a projection matrix, then some properties of the projection matrix, that some important condition it has to satisfy. First thing is that P transpose is equal to P, and that you can check that if I take A transpose A inverse A transpose, so this can be written as A transpose transpose, A transpose inverse, and then transpose and A transpose, and this is equal to A, and I know that A transpose I can write as transpose inverse A transpose, and A transpose A is symmetric, we already know. Then this is equal to again A inverse A transpose. So this is again the P. So it is symmetric, because we are taking the projection and taking the transpose, so it does not matter. The second one is that if we take the projection 2 times, now if you see from here, if I have taken the projection of this vector and it reaches here, now I apply the same projection here, it is not going to change, because this vector is already in the subspace S. It means that my P square should be equal to P. So let us see this one. So P square is A transpose A inverse A transpose, I write this one, and then A transpose A inverse A transpose, and this is I can write as A transpose A inverse A transpose A transpose. And if you see from here, I just take these two, then this is I, and from here I can write, so I can write here, then this is A transpose A inverse A transpose, and that is equal to P. So, it is p square is equal to p. So, from here we can see that this is my projection matrix. So, now the things is that how we are going to solve the system. So, this system we are going to solve. So, in the nutshell what we can say that now we have a system A x is equal to b, and this system is inconsistent, and this system is coming from least square. Then we take A transpose A x is equal to A transpose b, and from here, and we found that A transpose A is invertible, and we found A transpose A transpose b. So, this x we get this value. So, this x is x hat, and that will be the corresponding approximate solution. So, this is my approximate solution of A x is equal to b. So, this is the solution. After doing this one, we get that this matrix or this line will pass through the data closest to all the data. So, that is the meaning of least square. So, let us just quickly I will do one example. Now, suppose I have the data points 0 1, it is 1 1, it is 2 1, 3 1. Suppose I take 4 points, and these are data points. So, the question is fit a line. So, we want a fit a line. So, let I take a line y is equal to a x plus p. So, from here I will get my system a into 0 plus b is equal to 1, a into 1 plus b is equal to 1, a into 2 plus b is equal to, I just take, no it is, I have taken 3, now I just 4 and 4, this is the data point I am taking 0 1 2 3. So, 0 1 2 3, and this is 1 3 4 4. Suppose I take these points. So, I get the matrix A as 0 1 2 3 1 1 1 1, it is 4 cross 2, and this is my A B, and this is 1 3 4 4, this value I have taken. So, from here I have a system A x is equal to b. This is my system. Now, I want to solve this system. So, I will use the octave for this one, because we have to do a lot of calculation here. So, in this I will just, because and any student who has a difficulty with octave or MATLAB, then he or she can take the help of my another course, that is scientific computing using MATLAB. So, you can go through that few videos that teach that how we can work in MATLAB or octave. So, now we are going to define the matrix A here. So, this is the matrix I am going to have. So, matrix is basically I am writing 0 1 and then 1 1 and then 2 1 and 3 1. So, this is the matrix we got. Now, on the right hand side I have a vector B. So, that is the column vector. So, I will just take the vector 1 3 4 4. So, 1 3 4 4 this vector. Now, I know that I want to just check that whether this is going to have a solution or not. So, what I do, I found the augmented matrix. So, I just write AA, that is the augmented matrix, and that matrix I can write as A here and then B. So, this is my augmented matrix, and there is a inbuilt form, that is row reduced echelon form of the matrix AA. Okay, so, this one is I just write. So, I found this value. So, this is basically, from here I found that the system is inconsistent because the rank of AA, if you see the rank of AA is 3 and the rank of, if I found A, then you can check from here that it is 2. So, the system is inconsistent. I can write that system is inconsistent. Now, what we need to do? We have to apply the least square method. So, what I want to do is that now I will take the matrix. I get the matrix. First I found the transpose. So, I will take A this into A. So, that is my matrix A transpose A. So, maybe I can write here, I can just write B is equal to transpose, because some commands may be not here. So, it is a transpose of the matrix B. So, I can write here B into A. Actually, I have not written the star here. So, no problem. So, this is my matrix, and I know that this matrix will be invertible. So, I need to find the solution. So, I have to solve this one. Now, to find this solution, I have to find A transpose A x is equal to A transpose B. I have changed the system basically, and now from here I can find x bar is, this is my A transpose A inverse A transpose into B. So, that will be my solution in this case. So, I need to find out this value. So, this is my inverse. I have taken A transpose A. I just found the A transpose. This one, now I want to find the inverse of this. So, I can find, I can write inverse of B as inverse of the matrix B. B star A, not B, B star A, or I can write this answer ANS, this one. So, that is my inverse. Now, from here I can write now the inverse B, because I need now we have A inverse B into A transpose, because I need to find. So, I have taken this value, now I have to multiply by A transpose into B. So, this one I need to do. So, I have to take multiplication. Now, first I will do I just take this matrix and multiply by A transpose. So, that is B. So, this is my matrix, and now I just take answer and multiply by B. So, that is my solution. So, from here if you see that A is 1 and B is 1.5. Now, if you see from here, my x bar is coming 1 and 1.5. You can see from here 1 and 1.5. So, which implies that my line is A is 1. So, x plus 1.5, that is y is equal to this one. So, that is my line, because A value, the value of A is 1 here and B is 1.5. So, this is the line which going closest to all these points. It will never satisfy these points, because if you put x equal to 0 here, y is 1.5, but our data point was 1. If you put x equal to 1, y will be 2.5 and our data is 3, but this is the line which goes closest to all these points, and that is the least square solution. So, this is the I can say that the best line fit for the given data, and this is the way we can find out the solution of this type of least square solutions. Now, from this, so this way we can find all this one, and this is the way we have able to find the solution. So, this is the least square solution, and now I think we should stop now. So, in the today's lecture we have discussed a very important application about that if we have a data points, then how we can fit a line which is either passing through all the points, but if it is not passing through all the points, then it should pass closest to all the point, and that is done by the method of least squares. And then we have discussed that how, if the system is inconsistent, then how we can solve those system with the help of the projection. So, I hope you have enjoyed this lecture. Thanks for watching. Thanks very much.